Okay, it's recording.
Yes? Okay. Good morning. Hopefully everyone's staying healthy. As you all know, of course I'm allowed, as I mentioned 2.5 weeks ago, if you remember, 2.5 weeks ago, I said, be careful, there's a spike of COVID coming. Because it seemed like everyone I knew 2.5 weeks ago canceled plans one weekend because they all had COVID. So I figured that's not a random sample. But if they had COVID and they didn't know each other, it's coming here. And as you can see from the classroom, a lot of people have COVID. Again, that's really a big advantage that we record lectures so that if someone stays home either because they have COVID or because they're afraid to get COVID, as long as we're recording lectures and we take pictures of the blackboard, by the way, I'm going to close the shade here. That way you have access to everything. And you can, of course, ask questions at office hours or email me. And unfortunately, the geniuses in physical plant make sure that you can only open the windows at 6 inches. I don't understand why. Maybe they're afraid people are going to jump out. What can I say? Obviously not from this class. Okay, so are there any questions? I can't hear you. I would like to get back to the exam one. I just don't want to get back to 5 people or 10 people and get back to everybody. So, if people are okay again, I'll just have them in my office on Friday. People want to come up. You don't have class on Friday. So then on Monday, I mean, there are 2, 4, 6, 8 people here today. It's not fair to get back 8 people and not the whole class. So, what I would say is definitely Monday because people should be able to go there. So we should have at least 25 people here. It's one thing to get back to 25 people, and then we get back to 10 people, and then the other, there's 33 people in this class. So it's just, then I'll have, 25 people who are nervous. Because some people got their grades back and they were funny numbers, so what my grade. What I would say is, if you have any questions about the exam, ask me. We can have office hours and have to solve the problems on the blackboard. Or come to office hours like you were nice enough to do yesterday.
Is there a possibility to post the grade on Blackboard?
I'm sorry, with the mask on, I can't hear them.
Is there a possibility to post the grade on Blackboard?
Is what?
To post the grade on Blackboard.
Yeah, the problem is the numbers don't mean anything. I want you to see the comments. So maybe I'll do that on Friday. If I can't get to return the exam by then. I've never returned exams to only 1/5 of the class. It's never been an issue before. I've always returned it to like 90% of the class. And that way I explain to everyone what grades mean. This way, if I return and explain what grade means to you, what do I about all the other people? So, we're in uncharted waters here. So what I would say is, no matter what, you throw me 2 people here, I'll give up and just give it back to the next class. Even if there are only 5 people. Because I can't not give them back forever. Okay, other questions? All right, let's just review a little bit where we are and where we've come from. Again, if you're not wearing a mask, I advise you not to sit next to somebody, to sit away from other people. You have to stay there because of the camera. That means other people should get away from you. Or you should wear a mask. I'm guessing that guards probably have masks again.
Should I go? I don't want to ask. You could go away.
Okay, so let's just review where we are this semester. The name of the class is Process Control. We're recording the class here. And I would wait until the blackboard fills up because usually when I put out before class, there end up being mistakes that I correct. So you might as well, if you want to take a picture with mistakes, that's fine, but then you'll have proof that I made mistakes. I'd rather not have proof that I made mistakes. I'm not going to erase it before you take pictures, don't worry. here to help you, not to make life difficult, despite what you might think. So, okay, back to the class. So the name of this class is process control. What you may have noticed is we haven't done any control yet this semester. We're more than halfway through the semester, and what have we done so far? We've learned how to model simple systems, either linear systems or systems that are nonlinear that we then linearize. And then we refreshed our memory from ordinary differential equations and looked at how we solve linear or linear equations. So either coming from real linear models or models that were started out nonlinear that we linearize. And that was the subject of exam 1. After exam 1, we said, you know, maybe the algebra is kind of messy when we do things in the methods of ordinary differential equations. The algebra gets kind of nutty and messy. And with all that algebra, it's easy to make mistakes. Is there another way to make the algebra easier? So what we did is we introduced Laplace transforms, which are based in complex variables. And the first thing we saw was that it was an alternative way to solve linear problems. And the algebra was easier. And what it said was we started from a problem in the time domain. We Laplace transformed into the S domain, and the advantage of that is all the derivatives and integrals turned into just algebraic equations. So there were no more derivatives or integrals in time. And that made it much easier to solve the equations in the S domain than in the time domain. So we solved it in the S domain. Generally that was easy because they were algebraic equations, they were easier. And then, since we don't really care about the S domain, we wanted to transform back to the time domain to get something we're interested in. And to do that, we have a table with corresponding time domain, S domain pairs. And of course, any arbitrary function that we come up with might not be in the table. So what we try to do is break it up by what we call partial fractions into a sum of its most simple terms. Kind of like in elementary school, when you have a number and you find its prime factors. What you try to do is, if you have a big number, you try to break it up into the product of prime numbers. So here, this is the same idea. You have a complicated expression, and you try to break it up into the sum of its most simple pieces. Where you hope that each of those pieces you can find in the table, and then invert them. So we said, great, we have another method of solving ordinary differential equations. But then we went on and we said, you know, there are a lot of things we can do in the Laplace domain without even inverting. We can get a lot of information about questions we're interested in just from looking at the Laplace domain without even doing the inversion. So the first thing we noted was there was something called the final value theorem. That is, if there's a steady state, we can find the steady state without even inverting, just using the final value theorem. Then we also said, well, that's great, we don't even have to invert if all we're interested in is to find out, is there a new steady state or not, and if so, what is it? Then we also found out that the question of stability, is the reactor going to blow up? We can figure that out also. Is there going to be a runaway situation? We can figure that out as well from the answer in the Laplace domain without even inverting. And the stability, we say, we just look at the denominator, and we look at the zeros of the denominator of that plot of the answer in the Laplace domain. And we look at the zeros of the denominator, and we try to figure out, do they all have negative real parts? If even one of them has a positive real part, we're in trouble. Great. Then we say, is that all the information we can get from the Laplace domain? And it turns out, no, we can even get more information. Many times, the inputs are not just step functions or pulses, but you could have a sinusoidal input. As we saw, for example, let's say it's the temperature, which oscillates from day to night. It's cooler at night, warmer in the day. Or over longer time periods, it's cooler in the winter, warmer in the summer. So you have oscillatory temperature inputs. You may have other oscillatory inputs. Any sort of input into that bounces around, doesn't go way high or way low, even if it's not exactly a sine, can be broken up into a sum of sines and cosines. That's called the Fourier series. So if I know how to deal with the response to a single sine, I know how to deal with the response to a sum of sines for linear equations. So the question was, if I have a sinusoidal input with a certain frequency, what is the output? Well, we found that the output is also a sine, and it has the same frequency as the input, as long as the equations are linear. We also found out, we came up with an expression for the ratio of the amplitude of the output oscillation to the amplitude of the input oscillation. That's called the amplitude ratio. And we could write that in terms of the transfer function, g tilde, and it was just the magnitude of g tilde evaluated at s is equal to I omega, where I is the square root of minus 1. And omega is the frequency of the sinusoidal input. And finally, there's a phase lag between the input sign and the output sign. There's a phase lag, they're not in phase necessarily. And even that phase lag, we can determine without inverting. We just take g tilde, and we take the arctangent of the imaginary part over the real part of g tilde of I omega. So all that information we can get directly from the answer of the Laplace domain before we even invert. And there were simple formulas for those, and we proved that all those formulas tell us what we think they tell us. So that's just a big overview of what we've done from t is equal to 0 until now. The only thing I left out, aside from the details, was we also found that there were graphics. Sometimes we prefer pictures to equations. So if we can find a one-to-one correspondence between pictures and equations, and we know how to manipulate pictures, that can make the algebra much, much easier. And that's what we call block diagrams. And what we found was we showed how we could come up with a one-to-one correspondence between the equations in the Laplace domain and the pictures. These are called block diagrams. And we also had 3 rules how to do algebra with block diagrams. And that corresponds exactly to doing the algebra with, in terms of the equations. So the nice thing is, I can have a complicated system with lots of pieces of equipment all interacting. If I know the block diagram for each piece of equipment and how they hook up, I can do the algebra just in terms of the pictures, instead of doing pages and pages of equations. And moreover, all the information for the time domain is in the S domain answer. And the answer for the block diagrams is in the S domain. So we can either use the methods that we've come up with to take a complicated answer in the S domain, use partial fractions to break it up into a sum of its simplest pieces, and then look in the table to invert it. That's generally what we do. There's actually a computer program that does all that automatically, and that's called Simulink, and that's part of MATLAB. And one of the classes next week, either Monday or Wednesday, I will bring in my computer and hook into that thing, and we'll go through about half a period on how to use Simulink. But it's always good before you've used an automatic program to do it manually so you know what the program's doing, and that's what we've done so far. Okay, so that's sort of where we are. And before I go on to the next topic, which is control, finally we're going to get to control, I do want to mention that the systems we've looked at so far have been CSDRs, plug flow reactors without reactions, not very interesting, tanks with levels, and temperature control, either in a CSDR, where I have a fluid coming in and a heat exchanger, a coil, and a different temperature fluid coming out, or a house, or something with temperature control. In chemical engineering systems, as you know, and maybe I don't want to give you nightmares here, but in unit operations, one, I think it's called, I never remember which is one and which is two. You spend a whole semester looking at stage operations. Now, so for example, the distillation column. You could have a distillation column, we have a mixture of liquids coming in, and you have the liquid product coming out, the bottoms, and you can have a gaseous product coming out of the top, so you're separated. And generally, you have a bunch of stages in here. And what happens is the stuff in the bottom stage goes into a reboiler. The reboiler, you take some stuff out, and the reboiler puts the rest in. You take only the pure stuff out at the bottom, the stuff that doesn't reboil. And then at the top, when you have gas coming out, you might cool it, and some of the gas that doesn't condense, you take out as a gaseous product, the rest you put in. And this then separates the different species that you have. Now, how does this correspond to what we've done so far? Well, you can look at each stage in your system as a separate stage that you model. And of course, in your operations class, you do models of each of the different stages. You make many assumptions in order to make it tractable. So, for example, you may assume that the liquid level is above the weir. The weir is the thing that keeps garbage from settling down. And then the gas flow level is negligible. You assume constant low-level overflow. You assume make all sorts of assumptions here. And what we know so far from what we've done is that when the models are linear, then we can do control. Well, a lot of what's going on in, say, a distillation column or another kind of separator, there are also the nonlinear effects, but many things you can linearize. And I'm not going to go, there's a whole, like about 3 or 4 pages in the book talking about this, and I'm not going to go through it all in detail, this is mostly words. But generally, you do a balance on each stage, and you assume something like thermodynamic equilibrium on each stage. And you also assume, particularly with these stage operations, that any given stage only interacts with the stage above it and the stage below it, the adjacent stages, and not the stages far away. So you're always assuming that if this is the ith stage, that you have inputs and outputs to the I plus first stage, and inputs and outputs to the I minus first stage. But not to stages very far away, only to the adjacent stage. And so you will always assume things like constant relative volatility, equal molar overflow, that there's no heat of mixing or separation of the gas and liquid. You make many sorts of assumptions. And it turns out, so the question is, when can you linearize the models on each stage and do control on them in one of these stage operations? And there are some sort of rules of thumb from experience. Generally, if you're modeling, you would write down all the equations for each stage and then combine them and try to solve them. And that would be a very nonlinear problem. And we don't yet know how to do control on nonlinear problems. But if you can linearize, so anyway, so it would be a complicated, if you couldn't linearize, it would be a very complicated control problem. If you can linearize, then it turns out, when is it adequate to linearize? It's okay to linearize if you have a step input, say, in the input to your column. In a situation like that, you can do the linearization, but the parts that you really can't linearize is if you have significant reflux from the reboiler and significant stuff coming back from the condenser. If that is not, if those very slow streams, then you can still do your linearization and have something that's not too terrible. You also assume that the liquid holdup on each tray is pretty high, and that the gas holdup on each tray is fairly negligible. If you make these assumptions, you can get a linearized model that you can do control on. it turns out when you do that, the poles that when you write out the linear model and you try to solve it in the Laplace domain, it turns out the poles are all distinct. That is, you generally don't have multiple poles. Something like 1 plus st quad t squared. It's usually just products of things like 1 plus st pi. And generally the poles are real. But if there are poles, if you include the energy balance, then you may get some complex poles, but usually the coefficients of the terms with the complex poles are usually small. So they're usually those up. Remember, the solution, you typically get a sum of terms, each one of which looks like a coefficient times an exponential. If the exponent is real, then it either is an exponential growth or an exponential decay. If the exponent is complex, it's an oscillation that either grows or decays, if the real part is positive or negative, or just stays a natural oscillation if the real part is 0. If the coefficient of that is very small, then as long as the exponent, the real part of the exponent is not positive, then that term is overshadowed by the other terms that have much bigger coefficients. What else can I say about this? Another thing is the solution can, remember we said the solution of a Laplace domain you often write as a numerator over a denominator. And if both the numerator and denominator are polynomials, which when you linearize you'll get in these types of systems, then what we say is generally the first thing we do is we cancel the like factors in the numerator and denominator. They don't share any factors. As it turns out, for these systems, from experience, even though the poles are not exactly the same, so you may have 1 plus st in the numerator and another 1 plus st prime in the denominator, even if the t and t prime are not exactly the same, very often in these systems, there are the t's in the numerator and a bunch of the t primes in the denominator are so close that they almost cancel. Meaning, instead of a system that looks like 10th order, it may act like a system that's only 3rd order. What does that mean? If you remember, when we had CSTRs in series, that was the simplest case of an nth order system. An nth order system would be if I had n CSTRs in series. If you remember, if I have only one CSTR, then if the input is a step function, then the output is not a step function. The output is something that is a discontinuous first derivative. So the input is discontinuous. The output has a discontinuous first derivative, but it's continuous. If we have a second order system, the first derivative, the input to the second reactor has a discontinuous first derivative, but the output has a continuous first derivative, but a discontinuous second derivative. And if I have n CSTRs, an nth order system, then the n minus first derivative is continuous, but the nth derivative, the output is the nth derivative, that's the discontinuity. So as you push things further and further down the line, the higher the order system, you push that discontinuity to higher and higher derivatives. And what we find is that in these systems, because the numerator and denominator have roots that are very close but not exactly the same, even though you would expect a 10th order behavior, it ends up behaving more like a 5th order system because those factors almost cancel. Another thing to note, if you remember, we spoke about interacting systems in series and non-interacting systems. A non-interacting system in series was like CSTRs in series. That is, the J CSTR gets inputs only from the J minus 1, not from the J plus 1. So the J CSTR I can solve completely if I know what happens to the J minus first. I don't need to know anything about the J plus first to solve the Jth one, because it only has inputs from the J minus first. And that's what we call non-interactive. And we said that the overall transfer function was just the product of the individual transfer functions. Well, you can notice here that But that's not the case in a column, because you have inputs from the I minus first as well as from the I plus first. So this is something that we would call an interacting. This is interacting. Series of trays. And if you remember last time, we saw that an interacting system, the individual trays have real negative roots, then, or real with negative or real negative roots, then the interacting system also has real negative roots. So it's just as stable. The issue, however, was that we said that the interacting system is much slower. That is, even though the product of the two roots is the same, the difference is much bigger. So the example I gave was if you're looking at the number 20, 5 times 4 is 20. They're pretty close together. You get the same 20 by multiplying 20 times 1. Also is 20, but they're very different. And and remember, each of the roots is coming in an exponent. E to the t minus t over 20, e to the minus t over 1. So if I have because the biggest root is much bigger in an interacting system than in individual non-interacting and individual systems that get put together to that interacting system. The response, even though the response to any given tray is fast, and typically the response of a given tray can be in tens of seconds, much less than a minute. But the response of the whole column is that particular effect on steroids. The column can respond in hours, even though individual trays respond in tens of seconds. So, and that's because exactly what we spoke about last time, that interacting systems are much more sluggish than the non-interacting systems. The final thing I want to say about these tray systems is that the value of the actual operating, the dynamics of the system depend very much on the operating conditions. What does that mean? That means if I change the operating conditions, if there's a big perturbation, I go to a new steady state that's very far from the old steady state, then I can't use, if I linearize the system around the initial steady state. So remember, when I linearize, then I assume that for all my calculations, things are going to stay fairly close to that linearization. Because the linearization approximates a nonlinear curve by the tangent, and the tangent is only good close by. It's a bad approximation far away. So in these particular systems, the curvature of the function that I'm approximating by the tangent is high. So that means when I change steady states, so for example, I was operating at one particular flow rate. Then the flow rate went up by 20%. It comes to a new steady state. If I want to describe what happens to the next perturbation, I can't use the linearization I started with before the step change. I have to do a new linearization about the new steady state. Because when I change the steady state, I change the operating conditions. So any nonlinear functions that I linearized, I have to throw out the linearization about the old steady state and linearize about the new steady state. Because if I had a curve that looks something like that, my initial steady state is here, and I use this as my derivative, and my new steady state is here, this derivative is very different from this derivative. So I better not use this tangent as an approximation. Once I move over here, I have to find the tangent again. And that's basically what this is. So you're welcome to read that. I spent sort of a half hour chit-chatting. But that's sort of the basis of what's going on in the stage operations. And at the end of the day, what the whole discussion is, how can we use the models that we've come up with so far for a stage system? And those are the intuitive things I'm trying to get across to you from experience of how what we've spoken about so far generalizes the state system. Are there any questions? Now, this concludes the material on how we model and analyze a model. So far, we've been passive observers. What is a passive observer? We're watching what's going on, and we're not affecting what's going on. We're just trying to figure out what's going on. We have a system, it's there, my CSDRs, my heat exchangers, and it's operating, and we're trying to model what's going on. We're trying to see what's happening and maybe predict what's going to happen in the future. But we're not touching the system. We're staying away from it. Well, it's time to change. The name of this course is process control. Process control is active. It's not passive. Control doesn't mean I watch and I see what happens. Control means I try to affect what's going to happen. There was a famous, there was a real example of control experiment that was in the news about 2 weeks ago. I'm sure you probably all heard it, that there was a part of an asteroid that what NASA did was said, well, sometimes, like what zapped dinosaurs, sometimes an asteroid comes and smashes into the Earth and causes a big disruption. So for example, the theory of Alvarez, which ended up being, is pretty much accepted now. Alvarez, who was a Nobel Prize winner in physics, and his son, who was a geologist, came up with a theory in the 1980s, so it was about 40 years ago, that where the title of the talk they gave was "What Zapped the Dinosaurs?" And we all sort of accept this today, but this was the idea at the time, was that an asteroid, that all of it, what's known from the fossil record, is that there were dinosaurs all over the place, and then at some point in a very short period of time, on geological scales, in a matter of years or tens of years, most of them died out. And what happened? So what the Alvarez theory was that an asteroid big enough that it made it through the atmosphere and crashed into the Earth, the last one in Mexico. And what crashed into the Earth might have only been a few miles wide, but that's still pretty big. Threw up so much debris into the atmosphere that it shut off the light. It basically interfered. There was so much debris in the atmosphere that it blocked a lot of the sunlight, a lot of the vegetation died, and then the dinosaurs starved. And in order to prove this theory, or to give information for this theory, it turns out that asteroids, many asteroids, have a much higher concentration of an element called iridium than is naturally found on Earth. So what people had done, or what they had people do, is to dig down far enough into the Earth to a time period corresponding to when the dinosaurs died out, and look to see if there was a thin layer of high concentration of iridium, because a lot of that debris was from that was in the atmosphere, was from the asteroid, and then sunk to the ground. And indeed, that was found that in various time periods that corresponded to mass extinctions, that there were layers that were enriched in iridium. And that's why people believe this theory today. Well, what's the upshot of that? The upshot of that is, every now and then some asteroid comes and hits the Earth, not every week, but maybe, every 100 million years or 50 million years, and we don't want to go extinct like the dinosaurs. I don't want to, I don't know about you. So what did NASA do? They said, maybe we can do active control, not just model with Newtonian physics that the asteroid's going to come and we give the date that it's going to come. Unlike some religious groups that don't do the physics and still say the Earth is going to end at a certain point. But maybe we can do control and move the asteroid, change its trajectory so it doesn't hit the Earth. So they did an experiment where they sent a rocket quite a ways from Earth to try to basically take a projectile and have the rocket as a projectile crash into this piece of an asteroid and change its trajectory. And there was this wonderful video, because it had a camera, where you could see how well aimed it was. It just went right for this asteroid, see the asteroid getting closer and closer, and then it goes black because it crashed into the asteroid. And so they managed to do their control. We would call that the final element. The final element, as you'll see, is what actually does the control at the end. It's the actual act. And they indeed found that it changed the trajectory of the asteroid, or at least of that rock from the asteroid. So that was a practical control problem, and there's probably no more important for humanity control problem than that. Anyway, this is not a course in geology, but I did want to give you a practical example. Notice I have been writing equations today. Something's wrong with me today, right? Let's talk about control. Control, again, is a situation where we stop being a passive observer and now we're going to act. We want to get 95% purity of product. The product is coming out 90%. Do we throw our hands up in the air and say, oh well, the customer doesn't want to like it, so the customer won't buy it. We'll get Elon Musk to buy it, he'll buy anything. No, we don't do that. We say, we're going to do control, and we're going to make sure that that conversion gets back up to 95%. How do we do it? So we need a little bit of background. Now we know how to analyze systems. We know how to analyze systems without control, and that same method of analysis will help us analyze systems with control. So we might have a system that without control is unstable, might blow up. We're going to put control on it so it doesn't blow up. And we're going to use the same analysis to show that the new system has poles only with negative real parts instead of the old system that has positive poles. So the goal of control is not just stabilize, keep the system stable, and get the product specs that you want. Okay. So you can see I can preach also. This could be, if there's an opening at the Abyssinian Baptist, there is, so I can volunteer for the job. Okay. So what can we say there? So there's a little diagram I can draw here, show here. We can call this the overall process. Until now, there was an input and an output, and that was it. And we were able to, we said, something happens to the input, let's calculate what happens to the output. That's what we've been doing so far. Control says, that's good, but maybe the output isn't what I like. So what I'm going to do is I'm going to measure something, measure the output, and if I don't like it, I'm going to do something about it. And I'm going to change something in the input to get what I want in the output. Because what I measured, I didn't like. Another popular control system is that anyone see these people riding around with these segways? You know what a segway is? You don't want to know. These segways are these like little platforms with wheels on them, where people just stand on them and they lean forward and they go really fast forward or backwards. Now, do those people have really good balance? Maybe, but that's not what keeps them from falling on their butt or on their face. What keeps them from falling is when they lean forward, underneath there are sensors that sense that if we do nothing, the person's going to fall on their face. So what it does is it puts a restoring force to push them upwards. If they lean backwards, then it has a restoring force to push them forward. There's a control system. Again, if I didn't have a control system, falling on your face. With the control system, big shock with the segment going 20 miles an hour. Should still be around it, but that's a different issue. Okay, so those are control systems. And, okay, so I need a little bit of terminology. So this is often called closed loop, for obvious reasons. It's a closed loop. Without the control system, it's open loop. So open loop or closed loop. Those are that's terminology that we use in control, open loop and control and closed. So in order to actually do this, I need a little terminology. So the first use of terminology, so I'm not going to remember all this. So we've got the measured variables. So I have to choose my measured variables. What do I want to measure? So typically it's the thing I'm interested in, the concentration of the output. If it's a reactant, is it the concentration I want? The temperature of the room, or the temperature is the output. Or if I have a liquid level. These are the things that I want to control. Then there's also the manipulated variables. So the measured things are these. The manipulated variables are these. These are the things that I'm going to change to get the control, to get the measured variable to be what I want. So for example, in the CSTR, if the concentration of the output isn't what I want, then what I might do is pump a higher concentration of reactant into the reactor. So that might be the manipulated variable. Well, how do I do that manipulation? I might open a valve or close a valve. So that is the manipulated variable, might be the valve that opens or that I can open or close to put a higher concentration, more or less of the reactant, a higher or lower concentration of the reactant into the reactant to spike the reactant. In the situation with the level of the tank, if the level goes up, then what I might do is manipulate a valve that controls the inlet flow rate. I might try to, if the level's going up too much, I might try to close the valve a bit so less fluid moves in there. What I always want is I want to choose manipulated variables for each measured variable. I need to choose at least one manipulated variable. There is really, and I want that manipulated variable to have various properties. I want to make sure that it affects, so that a change in the manipulated variable changes the measured variable a lot. I want to make sure that if I make relatively small changes in the manipulated variable, that it has a strong effect on the measured variable. I don't want to have to call in the cavalry and change things a ton in the manipulated variable to be able to affect the measured variable. I want to be able to get that done fairly easily. I also want that changes in manipulated variable do not affect the rest of the plant. I want to make sure that I change the manipulated variable, I change some flow rate, and it doesn't screw something up in another part of the plant. So those are some basic obvious things. Then of course there are disturbance variables. Disturbance variables are the ones that are causing me problems. So for example, let's say I have a CSTR and I have the inlet stream from another part of the plant. And that inlet stream has a certain concentration reactant. Well, there's a problem in some other part of the plant, and now it's coming in with too little reactant. So the disturbance variable, if you remember, those are the things that until now, we've said there was a disturbance with the step function or pulse in something. That variable is the disturbance variable, and I need to what we've done until now is there was a disturbance variable, this guy, and we calculated the measure variable, but we didn't do anything about it. Now we have the disturbance variable, so we have the disturbance variable here. We've got the manipulated variable here. And in response to the disturbance variable that changes the measured variable, we manipulate a manipulated variable to try to make up for the disturbance the problem of the disturbance variable. And finally, how do we do it? We need an algorithm for control. And that's something we're going to talk about for the next few weeks, and about how to actually do that. Questions? Now we need to talk a little bit about timescales. If you remember, we said that delay is a problem. Why is delay a problem? Because we said, for example, in the shower example, if it takes time, so in that case, in the shower, the measured variable is the temperature of the water that's coming out. We measure it not with a thermometer, we measure it with our body, if it's comfortable or not. That could be a thermometer. The disturbance variable is someone on the 12th floor is started flushing their toilet constantly. So it's taking up all the cold water, and all of a sudden the water's coming out too hot. And I don't want to get burned. So I have a control variable where I turn hot water down and I turn the cold water up. If there's no time lag, so my measurement time is very quick. As soon as the temperature goes up, I feel it right away. So the measurement time is fast. And then I have turn the knobs, and if I get instant response, that's great. Then I can really control the temperature. If there's a delay, I can often overreact. I keep turning the knob, nothing happens. I turn the knob some more because I'm impatient, nothing happens. And all of a sudden, all of it comes, and I burn myself, and I freeze because I turn the cold water on too much. So time scales are important. In chemical engineering, there are going to be two sets of time scales. There's the process time scale. So that's, in this case with the shower, it's the amount of time it takes from the time I turn the valve until there's a noticeable change in the temperature. In chemical engineering, the process times are usually very slow compared with the measurement times. So what I'm measuring is really what's going on. So typically, that's often the case. So the sensors are fast, but the process is generally slow. In electrical engineering, which we're not, that's not the case. In electrical engineering, the actual process is just as fast and sometimes faster than the sensors. So the output of my measurement device is what was happening a few milliseconds ago. It's not what's happening now in the process. So that's a much more complicated issue, and that's why you have control courses in electrical engineering and chemical engineering, but the emphasis is different because in chemical engineering, generally the time scales and the processes are slow. So we have time to react. Whereas in electrical engineering, there's no time. They have to react much faster. So just to give you a sense of what's involved here, I copied this from the textbook. Here I have my process, just the process down here. Now, what happens in a process, I need to measure something. So let's say what I'm interested in measuring is the temperature. The measured variable is the temperature. So I measure the temperature, say, with the thermocouple. The thermocouples typically work from seconds to a minute. So they're pretty quick. You get a response pretty quickly. And the response takes temperature, converts it to millivolts. That then has to come to a display so I can see it. From the millivolts of the thermocouple, it gets transformed into a current of milliamps. 4 to 20 milliamps goes from a voltage to a current, and that current goes to a display. And the display displays the temperature. Those electronic pieces are pretty quick, generally seconds. And let's say I see 200, 300 degrees. Well, now I need control. So I have some algorithm, some computer, or some control device that then calculates what to do. Typically, this is going to, if I have a chemical plant, I don't want the controller right next to the equipment. Because if something goes wrong and the equipment explodes or something leaks out, it's going to destroy the controller. So I generally locate usually there's a control room that's far away. It could even be a mile away. When in pre-COVID days, and hopefully in post-COVID days, occasionally we'll do a plant tour. And I took students to the Bayway Refinery a few years ago in New Jersey. It's less than about an hour away from here. And there was a control room. The plant was like a couple of square miles. And there's a room, a little building with control that's in one corner of the plant. It's not next to the equipment. It's far away. So you have that control room. And it decides based on whether the ice is temperature or not. There's an algorithm that says what the response is going to be. You get a signal conversion. That is, feedback says, I need to do something. So I need to open some valve to cool the thing down because it's too hot. Well, how does that work? So the feedback sends a signal, and that signal has to get transported somewhere. And that signal is in milliamps. It's a current. Then, how do you increase flow rate? So you open and close a valve. Well, the milliamps is not going to close the valve. What you need to do is to have a compressed air line, pneumatic control, where the change in the signal, which is in milliamps, then it's turned into a pressure, and the pressure will control the valve. So the pressure is typically going to be between 3 and 15 psi. And that then causes the valve to either open or close from 0 to 100%. This valve that actually does the work at the end is called the final element. And it takes just a few seconds to respond. It's important to note that this valve could be 100 or a few hundred meters away from the process. Again, if something blows up, you don't want it to destroy the whole control system, or something leaks out. So there's a response time once the valve opens or closes of a few seconds until you see a difference. So you have this whole system here, and you have many different time scales. Notice all the time scales here are seconds or minutes or shorter. Typically, processes in chemical engineering have time scales of hours or days. So all these other times are fairly negligible. Sometimes that's an exception, and the process gets out of control much quicker. So we have to be prepared for that. Are there any questions on that? Well, one thing to note is that since I have, notice you can think of this as processes in series, as non-interacting processes in series. I've got the process to the thermocouple, to the display, to the feedback, to the signal converter, to the IP that turns into compressed air, to the valve. Every step along the way depends on what came before it. So these are non-interacting systems in series. If I try to model these systems, each one of these systems will have its own transfer function. And since these are non-interacting systems in series, the G overall for this whole cycle will be the G of this, times 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 the G of that, the product. And presumably, most of these processes are first-order systems. But if there's a significant delay, if something is slow, I could have a series of non-interacting systems that have first or second order behavior with delays. And if you recall, if I have non-interacting systems, then I have in series, G tilde overall is the product of each of the individual units. So each of these individual steps. And some of these may have delays. So if you remember the overall delay, so first order system is maybe 1 plus SPI, the delays are theta I, theta j. The overall delay would be the sum of the theta i's plus the sum on j of the TJs. Because we said, if you remember, we said that 1 over 1 plus SPI is now equal to 1 over e to the SPI. Because this is the linear approximation to the exponential. And this is e to the minus SPI. And this looks like a delay. So when I multiply these together, then I end up adding up the TJs, and of course I have the natural delays, theta j, that come in as e to the minus s theta j, theta r. So when I multiply these together, I get the exponential of the sum of the thetas, and here I multiply these together, I get the exponential of the sum of the p's, and it looks like this, i.e. e to the minus s times the sum of the theta i's plus the sum of the pj's for the first order system. So this looks like one big delay with all this in there. This is all a review of what we've had before. All right, well, let's talk a little bit about by the way, we also want, when we choose manipulated variables, we want the response to be fast. And as we'll see, we like manipulated variables that can be controlled by valves, not something more complicated. Valves are very reliable. So we want involves a valve. So that's what we hope. We like valves. Okay, well, what are our goals? The detailed goals in choosing the manipulated variable and the control output. Now, we already spoke about the overall goals. The overall goals, of course, were safety, person safety, environment safety, equipment safety, etc. But what are the more detailed goals? Well, the detailed goals is, one, we want to minimize the difference between the set point and the error, which is the difference between the actual value and the set point. So obviously we want to minimize the difference between the actual value and the set point. And 1a, that means the offset. We want that to go to 0. Remember, what does offset mean? Offset means that sometimes I can put a controller on and I have a step change in the input, and I want the output to go to a particular value, but it reaches a steady state that's different from the value that I want. So that difference between the value I want and the steady state that it reaches is called the offset. So I want the offset to go to 0. I would like the rise time to be small. What is rise time? That means the time it takes to get to set point for the first time. So, for example, I want the rise time to be I'll overshoot. I'll go past the set point. So the rise time is the time it takes to get there the first time. But I might end up going up and down and crossing it many times. So there are different issues. The first issue is the short rise time. I don't want it to take forever to get to the set point. Even if it's going to overshoot, I don't want it to take forever. Now, how do I talk about error? Well, actually, let me go through a couple more issues. I want the decay rate. So I should actually look at offset. So offset, if this is the desired value, and my system looks like this, actual, this difference is called the offset. Rise time. So if this is desired, this is time, then this time is the rise time. It's the amount of time it takes to get to the desired value, set point for the first time. It may not stay there. That's the rise time. The decay rate. I want that to be small. So let's take a picture of that decay rate. Let's say this is again the set point. And let's say it oscillates and decays. The decay rate is the ratio. If this is A and this is B, it's how much I've overshot the first time and how much I've overshot the second time. The decay rate is B over A. It's the ratio of this peak to this peak. So I want that to go down to the peak. I'm not really that worried about the period of oscillation. My goal is to get rid of the oscillation, not the periods of oscillation. And then, of course, I want to keep the variation of the manipulated variable small. So I not only don't want the measured variable to fluctuate all over the place, I don't want to constantly be opening and closing the valve of the manipulated variable. Because if I'm constantly opening and closing the valve, the valve's going to break. So I not only think about the amount that the measured variable fluctuates, I also worry about how much I'm moving around the manipulated variable. So I don't want either one of those too much. Okay, so how do I measure the error measurement? How do I express the error? Well, one way of expressing the error is called the IE. That's the integrated error. Obviously, there's the instantaneous error. But the integrated error is just an integral of the difference. I'm going to call this delta. Delta T dt. This is the actual value. So if I just integrate the error up to t, I get the integrated error. Now that's not really a good idea, because if the error is positive and then it's negative, they're going to cancel. And that's going to say oscillating around the set point is a good thing. It's not a good thing. We don't want it to oscillate. We want it to step down. So this is, I hardly ever use this. I don't like that one. I prefer something that doesn't have negatives canceling positives. So one way of doing that is the integrated absolute error. So that's equal to 0 to t of the absolute magnitude of delta dt. So I get that way the negatives and positives don't cancel. The only thing I don't like about the absolute value is it's not differentiable. Whenever I hit 0, the absolute value is not differentiable. So if I have a controller that's doing some sort of algebra in it, doing calculation, I would like derivatives to be continuous. So I could do the integral square error. That's the integral from 0 to t of delta t squared d2 prime. So that way, I get, again, the negatives don't cancel the positives, but the square is differentiable, whereas the absolute value is not differentiable at 0. And finally, I might want to have an expression for an error that gives me a penalty if there's an offset. If there's a penalty, if it never quite gets there. It gets close, but never gets there. So I want something that's really going to force me to get to the answer. And that's called IT. 80, is it? Yeah, IT 8. And that's defined as the integral from 0 to t of the absolute value of delta t prime, but times t prime dt. So if there's an offset, so delta doesn't go to 0, well, I want a big penalty. The longer delta t doesn't go to 0, the worse the penalty is. It's a multiplying by t. So that really gives me a big penalty if things last forever. Now, what kind of disturbances do I typically have? Well, I could have steps. I could have pulses. I could have sign disturbances. I could have statistical disturbances. I could have just things bouncing around. So where for statistical disturbance, I can have the mean of the control variable. This is the measured variable, is the one I want